Good afternoon. Is everyone here, I hope? Welcome to the October SWS Webinar Speaker Series. Today's lecture and topic will be Salt Marsh Adaptive Management to Sea Level Rise using Runnels, presented by Dr. Alice Besterman. For those of you not familiar with our SWS Webinar Series, our monthly webinars are usually held on the third Thursday of the month at 1 p.m. Eastern Standard Time. As you can see on this listing of webinars, we have both our regular webinar series in English and also have quarterly webinars offered in Spanish, which are open to members and non-members alike. Our webinars are also posted to YouTube for free viewing when we have an amazing library of over 60 different webinars. Another expansion of our program is the development of wetland interviews, so make certain to keep that on your radar as well. Forward, please. We're proud to recognize our SWS Webinar Series sponsors for 2021, who include the Whittington Group, which is a natural resource consulting firm that balances regulatory compliance with sound ecological management, and HDR Incorporated, who specialize in engineering, architecture, environmental and construction services with multidisciplinary teams of scientists, economists, builders, analysts, and artists. You can find their information at the websites listed above. We'd also like to recognize In Situ, whose monitoring equipment and software work together to make it easier and more cost-effective to collect, access, and manage data on water levels, water quality, water flow, and more. Delta, who is an environmental restoration, mitigation, and land management company, provides complete and comprehensive mitigation services to both private and public industry throughout the Gulf Coast region. And finally, WildNote, which is a field data collection app for environmental professionals that streamlines the process of collecting, managing, and reporting environmental data so you can work smarter, not harder. Please visit, like, and follow our SWS webinar sponsors. Since January 2018, SWS webinars have been approved by the SWS Professional Certification Program for continuing education credits. These credits can be applied to your professional wetland scientist certification or renewal, or other certifications for that matter. Participation certificates are available through an automated process to those who watch the webinar in its entirety. You will receive an email about 1 day after the webinar, so please check your spam box if you don't see it. These certificates are free to SWS members, and certificates are also available for those who watch webinar recordings, which can be found on our events calendar page or our YouTube channel, which is complete with multilingual captions. This webinar is pending credit approval, so please be certain to monitor your email or feel free to contact SWS for status through our website at sws.org. Advance, please. Thank you. Okay, before we get started, I'd like to go over a few housekeeping items. For one, the general format for today's webinar will be a 45-minute presentation by our speaker, followed by approximately 15 minutes for question and answers. All attendees will be muted for the duration of the webinar. I just want to remind our panelists to make sure they mute their microphone and turn off their video camera when not speaking. Questions will be asked through the Q&A button shown here, not the chat button, but if you do have a problem, technical difficulties, you may enter those through the chat, and SWS staff will be monitoring the chat. At any time during the presentation, you can type your questions in the Q&A pane, and participants may upvote questions in the Q&A pane that they want to be answered earlier. As your moderator, I'll post the questions I received in the Q&A pane to the speaker. A survey will be sent to you via email from Zoom 1 day after the webinar. Please fill out the survey and give us feedback about today's webinar and the SWS webinar program. Additionally, please indicate if you'd be interested in giving a future SWS webinar. My name is Louis Mantini. I'm your moderator, and today's presenter is Dr. Alice Besterman. Dr. Besterman is a postdoctoral researcher co-appointed with the Buzzards Bay Coalition and Woodwell Climate Research Center, also a postdoctoral fellow with the Northeast Climate Adaptation Science Center. She received her bachelor's degree from Virginia Commonwealth University in Environmental Studies and her PhD from the University of Virginia in Environmental Science. Besterman is a coastal ecologist studying sea level rise and invasive species and their effects on ecosystems of conservation interest. Besterman's PhD research assessed the distribution and effects of an invasive seaweed on intertidal mudflat communities along the Virginia coast. Her postdoctoral work is focused on northeastern tidal marsh vulnerability and climate adaptation, along with project partners based at NGOs, state and federal agencies, and academic institutions. Besterman is focused on urgent and actionable science that will be used in coastal adaptation. With that, I'd like to hand over control to Dr. Besterman. Welcome, Alice.
Thank you. All right. Hi, thanks so much for having me today to talk with you about my postdoctoral work on salt marsh adaptation to sea level rise using runnels. So salt marshes are globally distributed productive systems. This map in the upper right corner shows the distribution of salt marshes in North America. They're characterized by dense stands of grasses and forbs, or zones or mosaics of dominant species. And they're experiencing rapid loss globally. This is of concern because salt marshes are important for many ecosystem services, including reducing nutrient loads in bays, providing habitat for fish and wildlife, and they also matter a lot to people. At the Buzzards Bay Coalition, where I work, we recently received an email from a resident in one of the bays in the Buzzards Bay estuary. They wrote to us saying, the marsh grass is dying off. This was describing the marsh near their home. They said the marsh grass is dying off in patches, leaving just mud that the water now flows into and is creating new smaller canals and rivulets when the tides are high. The grass die-off is a recent phenomenon, within the last year from what I've seen. The shoreline itself, which my property abuts, has not changed or been affected yet, though once the marsh goes, I would imagine that would soon follow. This area has brought us so much peace and joy, we are willing to do quite a lot to save it. So these areas of vegetation dieback in marshes and expanding shallow water have community members as well as resource managers and scientists concerned, and have led to the emergence of an adaptation technique to address these areas of expanding shallow water called runnels. This is a hydrologic modification, and I have a photo of one runnel shown right here. Now, while at first glance, this may look like a regular pan in a regular marsh, the context, functioning, and trajectory of these shallow water features we're beginning to see are different from historic pans and pools. So today I'm going to talk with you about marsh pans and pools, how they functioned in the past, how they seem to differ from the shallow water features we're seeing today, and what the future trajectories for these shallow water features might be. I'll introduce runnels as an emerging adaptation technique used in marshes, and I'll discuss whether runnels can be used as a method to buy some time for salt marshes into the 21st century. So pans and pools are natural features, are unvegetated and shallow water features in marshes. Pans form after some disturbance and are converted from vegetated marsh into an area of bare sediment with a characteristic forb community that differs from the surrounding vegetation. But they typically revegetate within 2 to 4 years. Pools, on the other hand, are deeper features. These remain flooded throughout the tidal cycle. They tend to be more stable, and if they do change, that typically occurs over decades to centuries. The dynamic for these pools is that one forms and then expands to some critical width, at which point a tidal creek incisors the pool and drains it, leading to revegetation in that pool, and the area returns to vegetated marsh. Because historically both of these features were thought to either remain stable or transition from bare to revegetated back and forth, they were thought to be in some kind of dynamic equilibrium with the vegetated marsh area, and that is not driving a net loss of vegetated area. To illustrate pool recovery, I have adapted this figure from Mariotti 2016. On the left, you can see these pools. The IP stands for isolated pool. And by 1991, you can see a tidal creek has become connected. The CP stands for connected pool, drained it, and it's beginning to revegetate. Looking at another pool, we see that this isolated pool has become connected and started to revegetate by 2015. Now, while this process has been observed in many places, it's also been observed that bare and shallow water areas are increasing in number and size across the Northeast and Mid-Atlantic. Features such as these are becoming more commonly seen in estuaries across these regions. These 4 photos are all taken in the Buzzards Bay estuary. I want to point out a few differences between these features and classic pans and pools. First, pans, as I mentioned, have a characteristic forb community. That requires that these features do drain regularly enough that salt marsh vegetation can recruit and survive, or these forb species can. However, the features I'm showing you here all remain inundated for too long for any vegetation to really successfully survive. In terms of they also are quite different from pools in a number of ways. Pools typically have unconsolidated sediments at their bases, whereas these features I'm showing you all have firm peat, indicating that they were recently vegetated marsh. They also do not have the stable boundaries that are typically seen with pools. Pools are often have fairly rigid, clear boundaries, whereas these features all look more raggedy, indicating they might be changing rapidly. These features also, while they do remain inundated for long periods of time, they drain fully during neap tides, and therefore they don't provide the same ecosystem services that pools do for fish and wildlife. And I've actually observed schools of dead mummichogs in these features when they have fully dried out before. So fish get trapped in them and they become too hypersaline, and so they're not providing those same services that pools do. As these features are beginning to increase, there have been a number of studies that are demonstrating these increases. One project in the Buzzards Bay estuary has found that by analyzing aerial imagery between 1938 and 2009, so far results indicate that pans have only deepened and enlarged, whereas pools have only expanded. These are preliminary data, but the patterns have been fairly clear so far. To illustrate this pattern in one marsh island in the Buzzards Bay estuary, I am showing you this one feature in 1954 on the left and in 2009 on the right. On the left, the vegetated marsh is indicated by white, open water by gray, and in 2009, the green indicates vegetated area and the blue is open water. By focusing on the shallow water features I've circled in yellow, you can see that the features in 1954 have enlarged and connected so that the total area of shallow water in this marsh island has increased. This suggests that we're potentially entering a new paradigm for marshes, one in which surface water areas are no longer in a dynamic equilibrium with vegetated marsh. This has been observed in many places. In Fire Island National Seashore, there was a doubling of pans that occurred and pools that occurred between 1994 and 2015. In the Blackwater River estuary, up to 21% of marsh area has converted to pools between 1981 and 2010. In Narragansett Bay, Rhode Island, between 1972 and 2011, 20 out of 30 marsh complexes had lost marsh area to interior ponding. Adamowitz and colleagues noted that while a few researchers have documented traits and trajectories of natural pools, the relatively sudden appearance and geographic extent of shallow pools and other marsh changes suggests a large-scale driver. So we've observed that these surface water features no longer appear to be in a dynamic equilibrium with vegetated marsh. There are a number of direct human modifications to marshes, as well as large-scale environmental drivers that are contributing to this phenomenon. In terms of direct human modifications, some of the most critical are shown here on the left. They include agricultural embankments, which were structures created in a marsh by colonial farmers to control the flow of water. The legacy effect of embankments today is linear ridges in the marshes left behind from where these structures were built. Ditches are extensive across the eastern coast of the Atlantic, or of the United States, where upwards of 90% of marshes have been ditched. This, of course, has dramatic effects on both marsh hydrology and geomorphology. The material excavated from those ditches was typically side cast or placed into linear spoils along the edges of those ditches, which again have formed linear ridges that impede water flow across the marsh. And finally, ditch plugs have been used as a method to counteract the over-ditching that occurred in the 1930s. However, more recently, it's been observed that these ditch plugs may be contributing to these shallow water features, and restoration ecologists are beginning to remove them and undo them. In terms of large-scale environmental drivers, the most critical is relative sea level rise, which is accelerating globally. Space to migrate inland for a marsh is also a critical factor in forming whether or not these surface water features are likely to increase and expand. So these shallow water features appear to be increasing. This raises a question about what their trajectory is, if they all will lead to net marsh loss, and what the different mechanisms of that might be. Mariotti in 2016 proposed 3 trajectories for pools that may be applicable to the shallow water features we're observing today. First is pool recovery, and this is the process I've already described, through which a pool becomes connected to a tidal creek, drains, and revegetates. This process keeps marshes in a kind of equilibrium with unvegetated and vegetated areas approximately equal, and typically occurs in marshes where vertical accretion is greater than relative sea level rise. In contrast, drowning and pool collapse are 2 processes through which these shallow pools or shallow water features contribute to net losses of vegetated marsh, and therefore are pushing marshes out of that equilibrium. They tend to occur where vertical accretion is less than relative sea level rise. Focusing first on drowning, this is a process of biogeochemical degradation. Water becomes impounded on the marsh, stresses vegetation, and leads to vegetation death. Live roots, which create much of the volume of the peat and build elevation, collapse, leading to subsidence within these areas of vegetation dieback. The elevation loss allows for more water to be held, and eventually these small fragmented areas of shallow water connect and lead to complete open water conversion. Drowning is thought to occur when the entire marsh platform is not keeping pace with sea level rise. This is in contrast to the pool collapse, which occurs through physical erosion of the pool. A pool becomes tidally connected, but instead of draining, as with pool recovery, the tidal creek connection leads to the pool enlarging and deepening. This occurs when the basin of that pool is not keeping pace with sea level rise. So essentially, whether the vegetated platform may have been keeping pace with sea level rise, but the elevation within this pool has become too low for revegetation to occur relative to sea level. This typically happens in marshes where there's very low sediment inputs. So without vegetation to build elevation in the pool, and without mineral sediment inputs contributing to this pool, the elevation gets too low and drainage and revegetation cannot occur. In pool recovery, as I've discussed, that tidal creek connection leads to drainage and revegetation. This can happen because the pool basin has been keeping pace with sea level rise. So typically this means that the marsh has adequate sediment supply to have been allowing this unvegetated area to keep building in elevation relative to sea level. To illustrate how this happens, I've adapted this figure from Shepherd et al. 2020. This tidal creek becomes connected to a pool, and at that point, the unconsolidated material at the basin of that pool becomes eroded by waves and tides and exported out through the tidal creek, allowing this feature to grow in size and to deepen. So I've mentioned that marshes where pool recovery occurs, typically the vertical accretion in that marsh is greater than relative sea level rise. But what does that translate to in terms of some other characteristics of these marshes? Mariotti's theoretical approaches in 2016 indicated that pool recovery is more likely to occur when you have a large tidal range, moderate to high sediment loads, and lower rates of relative sea level rise. We can also infer that because a hydrologic connection is required, that you're more likely to have pool recovery occur when you don't have these legacy barriers to water flow preventing movement across the marsh. And by that, I'm referring to those embankments and linear spoil piles forming those linear ridges that are blocking water flow. Empirical evidence has shown that all of these characteristics are not required for pool recovery, but we can infer that it is more likely for pool recovery to happen over drowning and pool collapse when you have some combination of these. Drowning and pool collapse are predicted to occur when relative rates of sea level rise are high. For drowning, you're looking at rates greater than 10 millimeters per year, and pool collapse from 5 to 8 millimeters per year. And while certain places are already experiencing these rates, the global rate of relative sea level rise is still 3.6 millimeters per year, indicating that we in many places are not yet facing irreversible trajectories down the drowning and pool collapse pathways. This suggests that we may be able to buy some time for marshes before either relative sea level rise becomes too high or before these shallow water features beginning to form become too degraded with unconsolidated sediments and deeper elevations of these pools, making it so pool collapse is more likely to occur. The implicit hypothesis of Runnels is that by taking an intervention now in marshes showing early signs of drowning or pool collapse, we can imitate pool recovery in marshes where it otherwise would not occur. So to summarize this first section, pools and pans were historically in something similar to an equilibrium with vegetated marsh area. But interactions between direct modifications made in marshes from agriculture and ditching and modern rates of sea level rise are leading to increases in shallow water area. If these features do in fact follow the predicted trajectories of pools, then we may be looking at a fate of drowning or pool collapse in these marshes without intervention. And so now I'll discuss how runnels are an intervention that may be useful for addressing this problem. Runnels are small channels that create a tidal connection between a shallow water feature on the marsh and a nearby creek or ditch. They follow topographical low areas or existing flow paths. And they operate as a Goldilocks solution. That is, not draining just enough to remove surface water from the marsh, but not over draining, which might lead to peat oxidation and otherwise harm that natural hydric soil condition of marshes. Here I am showing schematics of runnels in contrast to other mosquito control techniques. On the left is a figure adapted from Wolf 1996 that discussed various mosquito control techniques. Runnels have been historically used in mosquito control, and you can see by this illustration they are created to be much shallower than historic ditches, which range between 60 centimeters deep and 80 centimeters deep, whereas runnels here are shown to only be about 20 centimeters deep. In recent climate adaptation projects, the range of runnel dimensions ranges between these features here. So small runnels are typically on the order of 15 centimeters wide and 25 centimeters deep, and can be up to this wider runnel dimension of 60 centimeters wide and still only 30 centimeters deep. Importantly, these runnels are never created to be more than about 30 centimeters deep. As I mentioned, runnels have been used in mosquito control for the past few decades as an approach to manage standing water on marshes in a more environmentally friendly way than classic ditching. Since about 2010, Wenley Ferguson, the director of habitat restoration at Save the Bay in Rhode Island, has begun partnering with mosquito control and other restoration ecologists to pilot the use of runnels in salt marshes for adaptation. Since 2010, runnels have become there's a lot of interest rapidly growing in them, and there are currently runnel projects either in operation or in consideration in at least 6 northeastern states indicated in gray here. Runnels are currently being used in around 24 marsh complexes across these states. And while quantitative results are still limited, the majority of these projects have seen some revegetation within 2 years. So how might we expect the revegetation process to happen? So here I have a conceptual diagram of initial percent cover in a marsh experiencing shallow water expansion. Before runnel is installed, you can expect to see high aquatic conditions of shallow water and also algae and seaweed in many cases, as well as some bare area. After creating a runnel indicated by this red dashed line, you can initially expect a drainage phase where water levels will decrease rapidly and bare sediment will increase rapidly. This has the potential to lead to an initial loss of elevation and increased oxidation. Shortly thereafter, we can expect to see an increase in forbs, which will eventually level off in their cover, and Spartina alterniflora should begin to increase. At this point, we would expect elevation and oxidation rates to have stabilized. And finally, in a phase where we can begin to see some high marsh species recruiting, the early colonizers of forbs and Spartina alterniflora will have leveled off, and high marsh species such as Juncus, Spartina patens, or Disticlus will begin to increase. And at this point, we would hope to see an increase in below ground biomass and potentially some elevation accretion. To test these hypotheses, my research group has launched an experiment in the Buzzards Bay estuary to test runnels. And our primary research questions are here. First, do runnels consistently drain expanding shallow water areas? Second, do drained areas consistently revegetate? And third, do drainage and revegetation differ across gradients of platform elevation and peat degradation within shallow water areas? And by that, I essentially mean how broken apart is that peat and how much elevation has been lost in the shallow water area. We're working in 2 marshes that differ significantly in environmental characteristics, indicated by these red dots. We're using a replicated Bakke design study, and we have 5 experimental and 5 reference marsh sites in each of these marshes, giving us a total of 20 sites where we are collecting data. At all of our sites, we are collecting vegetation metrics. We have photo stations to monitor long-term change. We're monitoring water levels with Hobo onset high-frequency sensors. We're monitoring decomposition rates as well as elevation. At a set of 12 of these, of all of our sites, we are measuring a more intensive set of variables, including higher replication numbers of all of these variables and introducing some other additional environmental variables to be measured at those sites. Here I am showing you the 2 marshes where we're working. The green and purple lines indicate our monitoring transects, and each has been set up to bisect a shallow water area on the marsh. The purple lines indicate our experimental sites where a runnel has been installed, and the green lines indicate our reference sites where we are not going to be putting in a runnel. Our intensive sites where we have higher replication and more variables being monitored are indicated with these stars. We completed pre-monitoring of all of the sites in summer 2020 and began creating runnels in phases between October 2020 and February 2021. We plan to continue to monitor these for many years to come, at least through 2023, with hopes to continue for 5 or more years after. We worked with Bristol County Mosquito Control Project to create some of the initial runnels. Here you can see their low ground pressure excavator, which is specially designed to work in marshes. It exerts only 1.9 pound per square inch of pressure. And to put that in contrast, an average person exerts about 16 pounds per square inch. You can see that the elevation is quite shallow, or the depth of the runnel that is quite shallow where this excavator is working. And we intentionally created very shallow depths where the runnel intersects this dieback area. The excavator dimensions of runnels had a maximum size of 30 centimeters wide by 30 deep, and one of those runnels at that maximum dimension can be shown here on the right. Here on the right, I'm showing the same dieback area where we have extended the runnel using shovels so that we had better control to create some sinuous features in the runnel and also create it to shallower depths than was possible with the excavator. I'm showing you the same feature here on the left, so you can contrast mid-growing season with how this feature looked after creating the runnel. So far, we've completed our first growing season sampling of these sites. We have collected our data and are currently working on processing and analyzing it. Today, I'm going to show you some preliminary data and a few observations from the sites. Here, I am showing you the same feature where I just showed the excavator working. On the top is the feature in November 2020 before creating the runnel. And on the bottom is the dig day after creating the runnel. And you can see that drainage occurs quite rapidly. This was the same day. Note these features here where you have, where it looks like there's been deposited peat. We did place the peat into these peat islands. And the idea is that these microtopographic features can create habitat for salt marsh breeding birds, such as the salt marsh sparrow and willet. And we are monitoring these peat islands for, and these marshes for change in faunal use. Here are photographs from this summer. On top, we see a photograph of the same feature in July 2021, and below that, the same feature in September 2021. So you can note that these areas within the dieback, the vegetation does appear to have increased in stem density. It looks more like there's higher cover, and the vegetation looks more vigorous than it did in prior to the creation of the runnel. Here I am showing you data from our Hobo water level logger deployed at the site. So I have on the left water levels from last summer. The blue line is the 15-minute water level data, and the red line is the minimum water level measured every 24 hours, which I'm using as a proxy for water table height. On the right, you can see the same blue line and red line for 15-minute data and minimum daily water level from February through June. So this is after the runnel has been created. Soil level is indicated by this dashed black line. So you can see that before the runnel was created, there were extended periods where water level was never dropping below the soil. There was standing water for days to weeks at a time, and the tidal signal was not completely clear for that reason. However, after the runnel was created, it does appear that that tidal hydrology has been reestablished, and every day the minimum water level does drop to the soil level or below, just below it. Here is a reference site to show in contrast. On the top, I am showing you a photo of this feature from September 2020, then a photo from July 2021 and September 2021. And again, this is a site where we did not create a runnel. So as you might expect, we're not seeing any very strong or clear differences. There's still shallow water and sparse vegetation with some bare areas at this site. Looking at the water level data from last summer and then this past winter and spring, we can see that these extended periods of inundated water, where water is above the soil surface, have continued into both phases. And now I'm going to show you one site that's a little bit funky. So here is a treatment site where we have installed a runnel. You can see that right here. I added this orange arrow so that you can see the same, to indicate the well for our Hobo logger in each phase. It's difficult to see in this first photo, and so I was using that as an indicator for marking location in the photos. So you can see in November 2020, there was these patches of bare areas that in both July and September photos from this past year seem to be filling in with vegetation quite nicely. What's interesting about this site is the hydrology didn't show such a clear story. So here we have water level data from last summer, and you can see that while the water table is close to the soil level frequently, we didn't have extended periods of standing water at this site. I'll point out that when we scouted this site in the winter and spring, there was quite a bit of standing water. So we might be looking at a bit of a seasonal effect at this location. After the runnel was created in this winter and spring period here, we can see that we actually had quite a bit of standing water at this site. So this is preliminary data, and this is an interesting one that raises questions about how hydrology and vegetation are synchronized in terms of their response to the runnels. We've also seen some initial evidence of a groundwater seep at this site, a fresh groundwater seep. So there's a lot of fresh water standing at this site, which leads to questions about how upland hydrology and precipitation may affect the formation of shallow water in marshes and the efficacy of runnels across gradients of upland hydrology effects. So while there's quite a bit to unpack with our experimental data, and we're really looking forward to digging into that, we do have some early impressions based on not only our experiment, but also 10 years of practitioner experience. So these early impressions indicate that runnels have a better chance for success when you're working in an area that has relatively higher elevation in terms of the platform, and also where the elevation of the shallow water basin has not degraded to be too deep. You have better success where the peat has not experienced too much degradation and is still quite firm. And also better success when runnel excavation is conducted in phases and when sills are used. And the reason for that is even when the peat is quite firm, some unconsolidated sediment typically is going to erode off of these shallow water features once you've created a runnel. Here I'm showing where some unconsolidated sediment has collected in a runnel. In many of these marshes, sediment is a very limited resource, and so we don't want to contribute to erosion problems in these systems. By working in phases, you can drain a little bit and then collect this sediment and redistribute it onto the marsh platform, either placing it in unvegetated dieback areas or scattering it across the platform. Capturing this sediment is also aided by the use of sills. So here I'm showing a profile from one of our runnels. And a sill is essentially just a little speed bump in the runnel where we have created a higher elevation spot to help slow water movement and trap sediment. So I've discussed how runnels are an emerging adaptation technique and how our experiment is aimed at answering some critical questions about runnel function and potential efficacy across gradients. So can runnels actually buy time for salt marshes going into the future? Thinking about this schematic, if you have a marsh with expanding shallow water, the idea here is that by creating a runnel, you can stop the process and trajectory of heading toward drowning and pool collapse and instead imitate pool recovery by having drainage and revegetation occur. But then what is going to happen? In the short term, our measurements of vegetation, water level, decomposition, sedimentation rates, bulk density, and shear strength of the soil and elevation should all help to understand what the trajectory for these features might be over the next 5 to 15 years. But over the long term, stressors are continuing to affect these marshes. Those include sea level rise, low sediment inputs to marshes, small tidal ranges, and impediments to migration, all of which we know contribute to the formation of shallow water and make marshes more vulnerable to vegetation loss. So runnels do not address any of those 4 large-scale problems. And so over the long term, runnels might buy some time, but other adaptations are likely still needed. One, for example, might be facilitating marsh migration, removing hardened stone barriers at the upland marsh boundary, or transitioning vegetation by removing woody invasives are some techniques that resource managers are using to help facilitate migration. Another technique is sediment placement, actually building up the elevation capital on a marsh to help it adapt to sea level rise. So while runnels are not able to address these large-scale problems and completely solve the problem of expanding shallow water in marshes in isolation, in addition to a holistic marsh management plan that includes other adaptation techniques, they may help to preserve marshes going into the next century. And so with that, I would like to acknowledge our funders, my project partners indicated here and their respective institutions, as well as a very large number of collaborators, students, and interns and landowners who have helped us make this work happen. And I will take any questions.
All right, Alice, thank you very much for a wonderful, thought-provoking presentation. And we do have a few, time for a few questions. First we have up is, have you had problems with invasive volunteers in the revegetation areas? And if so, how are you controlling them?
I assume that means invasive species such as Phragmites, and We have not had any issue with that. Actually, interestingly, runnels have been used in some cases as a way to help manage Phragmites, since Phragmites might be increasing in locations where upland freshwater sources are becoming impounded in high marsh areas like this one on the left. These areas can become fresher than they would be if they were connected tidally to a nearby creek or ditch. And so runnels have been used as a way to introduce more saline water into these locations and help to manage Phragmites. So we have, so far as I know, nobody who has used these so far has observed a problem of Phragmites moving in. In terms of fauna, there is some concern about crabs moving into these areas. So drained, bare soil within the marsh is great habitat for fiddler crabs. And while fiddler crabs are native and a part of marshes and we expect to see them, because these are already quite vulnerable marshes and the vegetation is struggling to reestablish, there's some concern that the extensive burrow networks that get created by fiddlers in these areas, in that gap space between runnel creation and revegetation, could compromise the ability of the runnel to actually be effective at promoting revegetation. So there are some folks that are sort of thinking about fiddler crabs, not as an invasive species, but as something that they might want to keep out during this revegetation phase. So far as I know, that's mostly something that's been talked about among resource managers, and there's some early experiments and projects looking at the effects of fiddlers in these dieback areas, but I don't, to the best of my knowledge, there's nothing conclusive about that known at this time.
Right. Now here's a puzzler. In any of the sites, did or could runnels increase hydrology or pool instability? In other words, make matters worse. For example, if sea level rise occurs more rapidly than expected, should runnels be detrimental?
Yes, and so I think where runnels have the risk of being detrimental is where you end up, instead of mimicking pool recovery, you end up mimicking pool collapse. So that means avoiding areas where the elevation platform is sitting too low in the tidal frame, and or where the elevation of the basin of this shallow water pool area is sitting too low in the tidal frame. In either of those cases, it's possible that by connecting a runnel, you would actually be accelerating the expansion of that feature. And so in advance of creating a runnel, it's important to get a good understanding for your local tidal range and for what the elevation of the platform and the pool basin is in that area. For our experiment, we are testing runnels. We have both a treatment and a reference site that were cited to be right at the boundary of what we thought might be possible in terms of a location that would recover. And so these are two locations that are low in elevation and where, the marsh is definitely struggling there. And so we have created runnels there as a way to try and see if there's kind of a boundary case where you can pull it back, or if they are actually too far gone down that elevation trajectory. And so preliminary evidence at those two sites is not super promising. It does not look like we're going to get much recovery. There hasn't been evidence of things getting worse, at least yet, but it's only the first year. So.
All right. Well, sticking with the did you shoot yourself in the foot theme, did you look at sedimentation rates in the pans pre and post runneling? Although runnels dewater the upper surface, allowing oxidation of the root zone, I'm just wondering if there's a net loss of sediment after runneling.
Yeah, it's a great question. We looked at sedimentation rates. Buzzards Bay estuary has very low suspended sediment. And we did look at sediment deposition in these features prior to runnel creation. And there was, I won't say zero. I don't have the measurements exactly yet, but it was very, very low. The traps that we had looked almost clean after 3 to 4 days of deployment. And we had replicate deployments for that. So sediment deposition appears to be quite low. In terms of losing sediment, there is definitely a risk of that. These are very, very organic soils. The organic content is between 60 and 70% at most of these sites. And so there's very little mineral content to be easily eroded. However, to manage that, we worked in phases. For many of these sites, we actually created just a little bit of drainage. For example, we would start creating a runnel intersecting this shallow water feature, but not connected all the way to the ditch. So it allowed some water to flow out that might just sheet flow then off the surface. So we would create it to that extent, return, look at what had happened, collect any unconsolidated sediment that was trapped in the runnel, and then extend it further. We also left sills and returned again to collect that unconsolidated sediment. And so I think that there is certainly a risk of that. And what I've understood from resource managers who use this technique is the best way to deal with that is using these management techniques and an adaptive technique to avoid losing as much as possible.
Cool. All right. Here's the yin yang. All right. We were talking about loss. Now we have an accretion question. Have you monitored the elevation of the peat islands you created from runnel spoils? Does their elevation lie within the local growth elevation range of high marsh plants?
Yes. So I wish I had included some of the photos of those islands because it is really interesting. So the islands were created so that they range from about 10 centimeters above the platform to about 20 centimeters above the platform. And there's just a really cool and wild community of plants that have colonized them, ranging from Salicornia to Iva to Disticlus and Patons in some places. And so we aren't closely monitoring the vegetation communities that are forming on those, but they are all revegetating rapidly. And, almost in the way marsh organs are used to look at how vegetation changes with different micro elevation differences, you could use these peat islands in the same way. So they are within the range of high marsh species at these sites. High marsh species are colonizing them. And it'll be really interesting to see how those communities evolve over time.
Awesome. So we're running close to short on time, but there's a couple more questions up, and let's see if we can get through them. Do you plan on trying to find the tidal range that supports runnel application? I think I understand this question.
Yes, the tidal range that supports runnel application. So we are working within one system with a very limited tidal range here. So the gradient is just, at one of our sites, it's about 4 feet. And at the other side, it's about 3 feet. So just about 1 meter at both of our sites. And so we're not going to be able to answer that question with this experiment. However, that is definitely something I'm very interested in. And there are folks working on runnels in the Gulf of Maine. And so I think contrasting there, where you have multiple meter, you have macrotidal conditions there of multiple meters of tidal range. And so I think contrasting our results with theirs is going to be really interesting. It would also be really interesting to look at even more compressed tidal range amplitude. So in sub 1 meter super microtidal areas, I think it'd be really interesting to see if runnels can have a positive effect. To my knowledge, I don't know of anywhere runnels are being tried right now that have that low of a tidal range, but I think that would be really interesting to understand and compare results.
Great. All right, last one. From a management perspective, runnels will require more frequent maintenance and recleaning than a deeper ditch. It'll be interesting to see how long your runnels hold up before vegetating in. Will you be monitoring that?
Yes, we are going to be monitoring that. And from folks who have been using runnels, I understand that I think they typically every 2 years make a trip to do some clean out. They do revegetate. They do fill in with unconsolidated sediment or pieces of peat that fill in, and that does compromise the amount of positive drainage you're getting out of them. And so I think the way people are, because this is being used in an adaptive capacity by a lot of NGOs and nonprofits, they're making a lot of use of partnerships with volunteers to go out and check on these runnels and make small changes at a time and clear them where some vegetation is starting to clog flow. But we will be monitoring the depth and width of them over time to see how rapidly they fill in and how quickly they revegetate within the runnel. Within 1 year, we haven't seen anything yet. They haven't started revegetating.
All right. We're going to have wrap up the questions and answers. If we could advance the slide, because I know that some of you will have questions, and Dr. Besterman has an email address that
I should stop sharing, right? Or advance. Sorry, I didn't have my email address up there. I apologize. I can type it somewhere.
Okay. Well, once you stop sharing, I think we will advance to another slide that does have your email address. And I just want to let everyone know that if you still have questions preying on your mind, please do contact Dr. Besterman directly through the email. And if we don't get the slide up, then at least we can, here we go. On the left panel, below the left panel, Dr. Besterman's email address is up there. And please contact her. So you can also get these slides through the website after the show if you don't get this information now. Please advance. I just would like to announce our next English speaking webinar in November will be presented by Dr. Laura Bourgeau-Chavez. Dr. Bourgeau-Chavez is a senior research scientist at Michigan Tech Research Institute and an adjunct assistant professor in the College of Forest Resources and Environmental Science of Michigan Technological University. Her webinar will be titled Peatland Mapping from Boreal to Tropical Zone in Americas. Please visit the SWS website, sws.org, or check out our social media channels to register for these upcoming webinars. Please advance. Be sure to follow, subscribe to social media channels of SWS, like Facebook and LinkedIn, to keep informed about and to support the society. If you're not a member, please check out our webpage and find out how to become one, and you'll get all the benefits of SWS membership. We also have a YouTube channel where all of our webinars are posted 3 months after their original broadcast with multilingual subtitles, and newly added over the past year are wetland interviews, 2 in English, 3 in Spanish. They're posted on our YouTube page as well. You can quickly link to those on the SWS website under the Resources tab and select Wetland Interviews. If you're Spanish speaking, be certain to subscribe to the Latin American and Caribbean regions Facebook page at the link listed there. And finally, thanks again, Dr. Besterman, and our webinar sponsors, and thank you to our audience for participating, and have a wonderful day and stay well.
Thank you, everyone. Have a nice day.
Thank you.